Now let us start study session 3, the applications of quantitative methods. The first reading is common probability distributions. In this topic we are going to study the definition of probability distribution, then the difference between discrete and continuous random variables. Then for specified discrete random variable, we will look at the possible outcomes. We understand the probability function, probability density function, and the cumulative distribution function. Then we look at the interpretation of probabilities for a random variable. We will define the discrete uniform random variable and binomial random variable. We will understand the probabilities given the discrete uniform and binomial distribution functions. Then we will learn to construct a binomial tree to describe a stock price movement. We will look at the tracking error. Then we will look at the continuous uniform distribution. And finally, we explain the key properties of normal distribution. We look at the difference between univariate and multivariate distribution. And we consider the role of correlation in multivariate normal distribution. Let us look at the other topics we are going to cover. Determining the probability that a normally distributed random variable lies inside a given interval. We'll take a few examples to understand it. Then defining the standard normal distribution and explain how to standardize a random variable. To understand the probabilities using the standard normal distribution. Then we will define the shortfall risk, calculate the safety first ratio, and the selection of an optimal portfolio using this criteria. Then we'll look at the relationship between normal and log normal distributions, and we'll see why the log normal is preferred for asset prices. We'll also distinguish between discrete and continuous compounding for rate of returns. And finally, we'll look at the Monte Carlo simulation and its major applications and limitations. So let us start with the first topic, which is discrete and continuous probability distributions. Let me explain what is probability distribution. This is a distribution function which tells us the probabilities of all possible outcomes for a random variable. For example, the outcome of the roll of a dice is stored in a random variable, say x. So the probability distribution will be giving all possible outcomes of x. For example, in this case, the value which this variable can store could be 1, 2, 3, 4, 5 or 6. There cannot be any other outcome except these 6 values. So these are all possible outcomes. So that says this is a probability distribution for this particular event. Now based on the values this random variable can hold, we have two kinds of probability distributions, discrete and continuous. If the random variable can hold only a finite number of values, that is, the number of possible outcomes are fixed, they are countable and measurable, then we define it as discrete distribution. For example, the number of days next week on which it will rain. So this is a random variable. It is a discrete variable because it can take only one of these 8 values. From 0 to 7, only these numbers it can take. It cannot have any other value, for example 8 or 7.5. All these values cannot be held by this random variable. So this is a discrete random variable. And this kind of distribution is discrete distribution. The example which we took earlier, the roll of dice, in this case as well, the x is a discrete random variable and we were talking about discrete probability distribution. Now let us look at the case of continuous distribution. As I said earlier, In this case, the random variable can hold any number of values, the infinite number of possible outcomes. For example, the amount of rain that will fall next week is a continuous random variable. So it can hold any value. There are infinite values between 0 to 50. There is a limit, but within that it could be any value. For example, it could be 14 inches, it could be 14.1, 14.12, it could be 14.121, it could be 14.1223, and so on. So there can be infinite values within this limit which this random variable can hold. So there is a function which will define this distribution. So this kind of distribution is continuous probability distribution. One important point about this probability is that at a particular point, the particular value of x is going to be 0. For example, the probability that the rain which will fall next week is going to be, say, 15.235, a particular number. This probability is going to be 0 because we know overall probability is going to be 1 for all the cases, and there are infinite number of cases. So for one particular case, probability is going to be very, very small, and we can say it is 0. Now let us look at various functions which define probability distribution. First is probability function. This is the function that gives us the probability that a discrete random variable will take. For example, if this is a function given, we have different values of x which this variable can hold. For example, it can hold one of these 5 values, 1 to 5. We can calculate the probability of getting any of these numbers. For example, for 4, it is going to be 4 by 20, which is 1 by 5. So using this probability function, we can calculate the value of the probability for any of the discrete values of random variable. So this is for the discrete case. The next important function is probability density function, which basically gives us the density of probability. And if we look at the graph of probability density function, in that graph, the area which falls below the graph gives us the probability. So this probability density basically is on y-axis, which helps us to find out the probability. This is used in a case of continuous random variable because there the probability at one particular point is going to be 0. So we have to use the probability density function so that we can calculate the probability between the range. For example, what is the probability that a value is going to lie between B and A? So that is defined by the area. So it will be this distance into this. So the area will represent the probability. Another important function is cumulative distribution function. This gives us the probability that a random variable will be less than or equal to a particular value. Let us take an example. If x is a parameter which is defined for the values between -10 to 40, and it is a cumulative distribution function fx, which is defined like this, x plus 10 divided by 20. So the question is asking what is the probability that x will be positive or equal to or less than 10. So basically the question which is asked is probability of x being less than or equal to 10 and a positive value. So this is the range in which the probability is being asked. We have cumulative distribution function, so we can calculate what is the probability of x being less than or equal to 10 and what is the probability of x being less than or equal to 0. If we take the difference, we will get the value. See here, this is defined by cumulative distribution function f10. Since from the definition of cumulative distribution function we know f10 indicates the probability of random variable holding value less than or equal to 10. So this probability can be calculated from this formula, which will be 10 plus 10 divided by 20. It will be equal to 1. So that means the probability that x will hold value less than or equal to 10 is 1. Now what is the probability that x will hold a value less than or equal to 0? Again, for less than or equal to, we should use cumulative distribution function fx. We'll put the value as 0. 0 plus 10 divided by 20, which is 1 by 2. So it is clear that probability of x having less than 0 is half, and probability that x will hold a value of less than 10 is 1. So that indicates the probability of x being greater than 0 and less than or equal to 10 is 1 minus 1 by 2, that is 1 by 2, or 50%. So that is the significance of a cumulative distribution function. Now let us look at the next concept, which is discrete uniform random variable. So we know the discrete random variable which can hold only a few values, and uniform random variable means where all possibilities are equally likely. That means the probability of all the cases is same. So in this case, the probability function will have a constant value. It will not have x as a variable. For example, in the toss of a coin or throw of a dice, we have limited number of possibilities, and if it is a fair coin or if it is a fair dice, we know the probability of heads or tails is same, which is 1 by 2. And in the case of dice, the probability of 1 or 2 or any of the numbers is same, 1 by 6 for all the cases. So these are the typical examples of discrete uniform random variable. In this example, the probability function says the probability is 0.24 for x equal to these 4 values. So probability for x having a value of 2 is 25%. So if we want to convert this into a cumulative distribution function and we want to know what is the probability of x having a value less than or equal to 2, or cumulative distribution function, this is how we denote it. So this value is going to be probability of x having value equal to 1 and probability of x equal to 2. So these are the two possibilities. Both of them are equal, 0.25, 0.25. The answer is 0.5. So F2 is 50%. And if we want to calculate probability for a range between 2 and 4, so we know this is equal to x equal to 2 plus probability of x equal to 3 plus probability of x equal to 4. There will be 3 cases, so answer will be 0.75 or 75%. So this is the distribution function which can be converted into any of the other functions as per the requirement. Now let us look at a few other random variables. Firstly, the binomial random variable. Binomial random variable can hold only 2 values within it, and this is used where we need to calculate the probability of exactly x success in n trials. As we said, the binomial random variable can only hold 2 values, which could be success and failure in this case. So where we have to calculate the probability of exactly x success or x failure in n trials, we use binomial random distribution. So the two possible outcomes are either success or failure. So if we know that the probability of one success is p, then if there are n number of trials, then the probability of getting success x number of times will be defined by this formula. I'll take an example. What is the probability of getting heads exactly twice if we flip a coin 6 times? First of all, let us define the distribution. We know this is a discrete random variable since it can hold only a few discrete values and it can hold only two values. So it is a binomial random variable and can hold only two values, which is heads or tails. We have to calculate the probability of getting heads exactly twice. So we are doing this experiment n number of times, or there are n trials, which are 6. We are doing 6 trials. Probability of getting heads in one single experiment is 1 by 2. We want to know what is the probability of getting heads 2 times out of 6. So we know n is 6 and x is 2. Okay, so the probability is NCX, the probability of getting heads to the power x into probability of not getting heads or probability of getting tails to the power n minus x. So in this case, the answer is 6C2, 1 by 2 to the power 2 and 1 by 2 to the power 4, which will give you 0.2344, the probability of getting exactly 2 heads out of 6 experiments. So this is the application of binomial random variable. Now let us look at the binomial tree, which will help us to understand the stock price movement. Suppose the price of the stock is S, which was say 50 in the starting. There are two possibilities: the upward movement or the downward movement. Say the value of u is 1.01. So if it moves upwards, the value becomes 1.01 into S, that is 1% higher, or in this case it is going to be 50.5. And similarly, we divide it by 1.01 again, which is the value of D if it falls. So the ds is 50 by 1.01. So if it further rises, again we multiply by u, that is 1.01. So the next price will be u into S. But if it falls, so we multiply by D, so it becomes u into D into S. So in every stage there are two cases. That is why we call it a binomial tree. So every time the variable can have only two values, up or down. So if in the first stage the stock has fallen, we have multiplied by D, and in the subsequent stage if it goes up, we multiplied by u. So u into D into S, which is nothing but S in case where u and D are inverse of each other. Again, if in the second stage as well the stock falls, we again multiplied by D, we get DDS. And similarly there could be two possibilities, up or down. In the case of down, we again multiply by D. In the case of up, we multiply by U. Similarly here, down, up, down. So we get these values. So using binomial tree, we can understand what should be the value after multiple number of stages. Then we can define what is the probability of going up, what is the probability of going down in all the cases, so that we can find out the expectation at different stages. So these are the expectations. Suppose we want to calculate the expectation at the last stage. So we need to look at the summation of probabilities into values. So this probability has to be found out. For example, let us say the probability of upward movement is 70% and downward movement is 30%. So this is 7.7, this is 0.3, and in the subsequent stages we'll keep calculating the conditional probabilities in order to calculate the expectations in different stages. For binomial distribution, the expected value of x is going to be n into p, where p is the probability of one single event and n is the number of trials, and the variance is defined by np into 1 minus p. So this is the simplified formula which can be directly applied if we already know that it is a binomial distribution. We can directly get the value of mean or variance. Now let us look at the another concept, which is tracking error. While declaring investment policy statement, we define a benchmark against which the performance will be measured and compared. For example, if there is a portfolio of stocks which gave a 5% return in the period, whereas the benchmark index performed better and gave 8% returns. So we need to calculate what is the tracking error of the portfolio, which will be actual performance minus the benchmark performance. So it will be minus 3% in this case. So negative tracking error suggests that our portfolio is underperforming the benchmark index, and the positive number of tracking error suggests that we are outperforming the benchmark index, which is the desirable behavior from an investment. So the tracking error basically gives us the idea about the performance of the portfolio. Let us move to the next slide. The continuous probability distributions. As we have already seen, in the case of continuous probability distributions, the random variable can hold continuous values, the infinite number of values, and since the value of probability at one particular point will be 0, we use the intervals here. So we have the probability density function and we define probability between an interval. For example, what is the probability of x holding a value between a and b? So that will be represented by the area when we have probability distribution function on the y-axis. There are various types of continuous probability distributions. Let us look at them one by one. The first is uniform distribution. The continuous uniform distribution is the one where probability is distributed evenly over the whole interval. So it can be easily defined by upper and lower bound variables. For example, if the random variable x is uniformly distributed between 1 and 11, we know that it is equally likely to have any value between these two. And since it is a continuous function, we can have any value even in fractions. So based on this information, which is the continuous uniform distribution function, we can calculate the probability for any other number, any other interval basically. So in this case, we want to calculate the probability of x between 5 and 8. So we clearly know that x is distributed between 1 and 11 uniformly. Say these are the values 1 to 11. So it is uniformly distributed. So if the probability density function is on the y-axis, so we know the value of density is constant. So this is the exhaustive probability value of the complete area, which is going to be 1. And if we want to calculate between 5 and 8, this will be proportional. For example, the probability of x being between 5 and 8 will be the total area will be in the denominator, which is 11 minus 1, and the expected area, which is 8 minus 5. So 3 by 12, which is 3 by 10, which is 0.3. So this will be the probability Similarly, in the graph below, it is shown that the shaded area is the one which is the favorable outcome, and the complete area is the total outcome. So we know this area A1, and if we say the total area is A, so the probability of value falling in this range will be A1 divided by A. So that will be the probability. Now let us move to the next concept, normal distribution. This is one of the most important, most useful concept in statistics. The normal distribution is the most important distribution, most commonly found distribution. It describes a continuous random variable. And we have already seen the properties of normal distribution, where we know the highest point is the mean, it is the mode, and the median. All three of them have the same value for normal distribution. It can entirely be described by mean and variance only. We do not need any other parameter. This is symmetric, so the skewness is 0. Kurtosis is 3. There is no excess kurtosis. We also call it mesokurtic. The another important property is if we have a linear combination of normally distributed random variables, then the combination will also be normally distributed. Suppose you know that there is a random variable A which is having a normal distribution. There is another random variable B which is also normally distributed. Then in any linear combination, for example A plus B, this is say C, another random variable, we know that this will also be normally distributed. Another property is the probabilities decrease as we move far from the mean, but the tails are endless. For example, if we draw the normal distribution curve, it will be something like this. There will be tails moving in both the directions till infinite. This is the point where we have mean, median, and mode. This is symmetrical and mesokurtic. The kurtosis is equal to 3. And as we see the probabilities, they are highest at the mean and they keep going down as we move away from mean, both on right side and the left side. The standard deviation determines the width of the curve. The larger values result in wider or flatter curves. For example, if we have this, so suppose this has a standard deviation of sigma 1. If we have this curve, this is going to have more value of sigma. Sigma 2 is greater than sigma 1. So again on the y-axis we have the probability distribution function, so that the value of probability is calculated as the area under this curve. So this is the density function. If we calculate the area using integration, we get the value of probability. So for example, this area says the probability of x holding value between a and b. So this area will signify the value of probability. So the total area falling under this curve will be 1. Since it is exhaustive, will represent all the values, so the summation is going to be 1. And since it is symmetric, the area on the right hand side is 0.5 and area on the left hand side is again 0.5. Let us move further. We look at the concept of confidence interval. Assuming that the random variable is following normal distribution, confidence interval will give us the probability that values will lie between a range, and this range is defined in terms of the standard deviation. Based on the distribution, the value of probabilities, we can define the confidence interval. For example, let us talk about this area first. So in the case of normal distribution, this area is 6/8. Since we know the total area is 1 and this particular area is 0.68. So we know that 68% of the values are going to lie in this range. This range is minus sigma to plus sigma around the mean. We can say if the value of mean is say 2 and the value of standard deviation is say 1, we know this value is Ex minus sigma, this is Ex plus sigma. So 2 minus 1 sigma, which is 1, to 2 plus 1 sigma, that is 1 to 3. So this is the interval. So if this value is 2 and the standard deviation is 1, so this value will be 3 and this value will be 1. So what is the probability of x having value between 1 and 3? So probability of x having value greater or equal to 1 and less than 3 will be defined by this area, which is 68% or 0.68. We can say that 68% is our confidence interval. In this case, we are 68% confident that the value will lie between plus minus 1 sigma from the mean. Similarly, for normal distribution, we know for 90% confidence interval, the value is 1.65 sigma. Or we are 90% confident that value is going to lie between mean minus 1.65 sigma and mean plus 1.65 sigma. Similarly, for 95% confidence interval, the value is plus minus 1.96 sigma, and for 99% confidence interval, the value is plus minus 2.58 sigma. So as the number of times sigma we have, higher is our confidence interval. So the area keeps enlarging as we move away on both sides. That represents larger size of the confidence interval. Now let us take one more example. It says the mean annual return, assuming it is normally distributed, for a portfolio is 10% and the standard deviation is 6%. We want to calculate a 95% confidence interval on next year's return. So what should be the expected return next year with a confidence interval of 95%? We know for 95% confidence interval, the value of sigma is 1.96. So we are 95% confidence that value will lie between 10%, which is the mean, plus minus 1.96 into sigma, which is 6%. So we'll get the range, which will be 10% plus minus, which will be 11.86%. So the range is going to be minus 1.86 to 21.86%. So this is our confidence interval of 95%. So this value is 11.86. Now let us look at the difference between univariate and multivariate distribution. As the name suggests, univariate distribution describes a single random variable, the cases which have been considering so far, and then there are multivariate distributions where we have the probabilities of a group of related random variables. So when we talk about normal distribution in the case of multivariate, in addition to the mean of all the securities and their individual variance, we would also need the correlation, pairwise correlation, and this will be the number of pairs. So this can be written as nn minus 1 by 2, which is nothing but nc2. So NC2 will be the number of pairs if we have n assets in our portfolio. So this is the case of multivariate normal distribution, where we are going to have more than one random variables. Now let us look at the specific case of normal distribution, the standard normal distribution. What is standard? This is a specific case of normal distribution which is standardized with mean to be 0 and standard deviation to be 1. If this is the case and the distribution is normally distributed, then we call it as standard normal distribution. And for that we have defined a z value or z value, which is number of standard deviations. So for calculating z, we subtract the mean so that it is standardized to 0 and divided by standard deviation so that standard deviation becomes 1. Based on this manipulation, we get value of z, which is the observation value minus population mean divided by standard deviation. So by reducing mu, we are making mean to be 0, and by dividing the standard deviation, we are making standard deviation to be 1. In other terms, as I said earlier, z is the number of standard deviations we are away from the mean. In the previous slides, we discussed that the distance of 1 sigma, 2 sigma or 1.96 sigma and so on. So these values are the z-scores or value of z. So using these values, we can calculate the probability. We have a table for the probability distribution. Using that, we can calculate probabilities corresponding to various values of z. We have seen a few values there. Similarly, we can calculate values of probability for all possible values of z using that table. Now let us take a few examples. The first example says the earning per share of a retail sector is normally distributed. It has a mean of 5 and standard deviation of $2. Now the question is asking the probability that a randomly selected firm's earning per share are less than 3. We know the mean of the population, which is $5. The standard deviation of the population is $2, and we know it is normally distributed. So the question is asking the probability of a randomly selected firm of having earning less than 3. So for value of 3, what is the z-score? Z is x, which is 3, minus mu which is 5, divided by sigma, which is 2. So the value is minus 1. So the question is asking what is the probability. This is the mean. This is 1 sigma. What is the probability of this value lying below this? So this is 3. So we want to calculate this probability. This is corresponding to z of minus 1. So we can look at the chart and calculate that this is 15.87% probability. So in our table, it can be given in multiple ways. If the area of rest of the part is given, then we have to subtract it from 1. For example, if we know that for plus 1, for z equal to plus 1, the value of this area is 0.8413, then we can simply subtract it from 1. So we get the value for z equal to minus 1. 15.87% is the probability that a randomly selected firm's earning per ratio will be less than 3. Let us move to the next slide. Here we talk about a few other ratios. First is the shortfall risk. This is the probability that a portfolio return or value will be below a target return or value. So if we say that the target return is 7% for our portfolio, so we say shortfall risk risk is the probability of X having value less than 7%. So what are the chances that the portfolio return will be less than the target return? So this is called shortfall risk, that will fall short of the target. The another important parameter is Roy's safety first ratio. So what does safety means here? Safety first indicates that there is a minimum acceptable level of return that has to be achieved in the portfolio without taking any further risk to increase the return. So this is the minimum acceptable level. So the formula for safety first ratio is return of your portfolio minus a minimum acceptable level divided by the standard deviation of the return of the portfolio. So this ratio basically indicates the shortfall risk. If it is higher, that says shortfall risk is higher. If it is lower, that says. So the safety first ratio basically indicates the shortfall risk. If the ratio is higher, that says the shortfall risk is lower. If the ratio is lower, that says the shortfall risk is higher. If we closely observe, this ratio is similar to Sharpe's ratio, where we were using risk-free rate instead of the minimum acceptable rate. So that is why that was another measure of return per unit of risk. In this case also we are measuring return per unit of risk, but above a minimum acceptable level. So that is the difference between the two ratios. So these parameters basically help us to understand what is the amount of risk we are taking for the expected returns. Now let us move to the next slide. Here we compare the normal and log normal distribution. As the name suggests, if X is the random variable for which the distribution is normal, for e to the power x, the distribution is going to be log normal. So there are different properties of log normal distribution. First, it is always positive. This is basically used for modeling price relatives. So whenever we have to perform any operation on the stock prices in econometrics, instead of using price P, we convert that into return, which is log of price divided by the previous price. So we take log of the return. So this log is actually normal. We know the stock prices do not follow normal distribution, they rather follow the log normal distribution. Another property of log normal distribution is it is skewed to the right and bounded by 0. The minimum value is 0 in case of log normal distribution, while in the case of normal distribution the minimum value and maximum values are plus minus infinite. But this is limited on the left side and unlimited on the right hand side. That is the basic difference between the normal and log normal distribution. Now let us move to the next topic, which is continuous compounding. Here we calculate continuous compounding rate from holding period return. As we already know, the holding period return is the final price minus dividend if it was given divided by the initial price. This will give us the holding period return. But if we want to calculate it in terms of continuous compounding, we use this formula. If we remember, the formula for continuous compounding was e to the power r minus 1. This was the continuous compounding. So we are getting holding period return here. If we take log of both sides, we will get log of 1 plus HPR equal to R, which is our continuous compounding rate. So the formula is same. We have just put that in another way. Now let us move to the next topic, which is Monte Carlo simulation. This is again a very simple and powerful method of simulation which helps us to estimate the distribution. Say for example of derivative prices or net present value or value at risk. It can be used for any other purpose. So for example, if we have a function, for example, is earning per share of a company, and we have a complex function for that which includes the interest rate and say the price of raw material, GDP growth rate or some other variable, and we know their distribution. For example, we know their distributions. For example, let us say these variables are normally distributed, so we know their mean, we know their standard deviation or variance. Similarly, M2 sigma 2, M3 sigma 3. So we have defined the distributions of the independent variables. Based on the distribution, the simulation keeps putting the values, various combination of values for these three variables, which will give us a large distribution of the dependent variable, which is EPS in this case. And we can look at this distribution, we can calculate the mean, variance, and we can look at the other properties and understand based on the distribution of input variables or independent variables what kind of distribution we will get for the dependent variable. So that is the objective of Monte Carlo simulation. It uses the computer generated values of variables based on the distribution given. So there are a lot of values, that is why the simulation is repeated thousands of times, and finally we receive the distribution of dependent variable. Now that brings us to the end of the topic. Let us take a few questions.